Hello, everyone. Let's continue with our discussion on two major topics. One is SVD, the other one is ICA. So SVD is called singular value decomposition, which is actually not new. I assume that you already have exposure there, especially in Chapter 2, we have discussion on eigenvalues and eigenvectors, etc., which is SVD really built upon those. So this is powerful output, right? Just be aware for any real matrix of A of size m by n can always be written as P times D times Q transpose. And then P is a m times m orthonormal matrix. You might be wondering what is orthonormal. We'll get to that shortly. And then Q is a n by n orthonormal matrix, while D is a diagonal matrix. By now, you probably already realize why we're talking about eigenvalue and eigenvectors. D would be composed by the eigenvalue information. So this is called SVD. In other words, any real matrix A can be decomposed into three components. First one is P, second component is D, third component is Q transpose. Once you have P, D, Q, you would be able to calculate your A. And then now let's look at what is orthonormal. A square matrix Q is orthonormal if it is orthogonal and each column is a unit vector. Each column is orthogonal to each other. And then each column has a norm being a one unit vector. So once that each matrix, if the matrix satisfies those conditions, then we call it orthonormal. And then we use Q times Q transpose. It's the same as Q transpose times Q should come back with identity matrix. In other words, Q inverse is equal to Q transpose, where I is identity matrix of same size as Q, and similarly we have P is orthonormal, so that P inverse equal to P transpose. So that's something you should know. And then the other thing you should know is for m by n diagonal matrix D, when m is not equal to n, then we define it as when I equal to dii would be equal to di, and then if I doesn't equal to j, then they would be set to 0. So you can see from this matrix, d1, d2, d3, but the rest of them would be 0, because it's really not a square matrix in this case for this D. This is just some special situation that you should be aware. Of course, there are all kinds of rigorous algorithms to carry out SVD effectively, and you can refer to those specialized literature if you're interested in how it works. But at least high level, conceptually, you know, any real matrix can be decomposed into three components, and this process is considered to be singular value decomposition, SVD. PCA is based on the second order statistics such as variance. Data projection can be carried out using SVD. If we can rewrite x tilde using the following SVD, x tilde is P times D times Q transpose. Our original covariance matrix, remember, it is C equal to 1 over n minus 1, x tilde transpose. We purely just use substitution of the x tilde by this quantity, and then we can come back with some manipulation, come back with that covariance matrix is P times, call this alpha, P alpha, P transpose. And then alpha is d squared divided by n minus 1. It's a diagonal matrix where diagonal values are eigenvalues of the eigenvectors. And P is really the eigenvectors. Eigenvector matrix. Therefore, the data projection in PCA is, instead of y equal to u tilde transpose times x tilde, it should be equal to u tilde PDQ transpose. So this means that PCA can be viewed as a special class of SVD. Okay, that's really just give you a sense on the relationship between SVD and PCA. That's SVD. Next, coming up, we want to discuss ICA. So let's think about one more case. Directions obtained by PCA are orthogonal and PCA uses mean and variance. We want to see it would be advantageous to use higher order statistical information for data sets, which is ICA. So what ICA does is, as its name stands for, ICA is really independent component analysis. So it's trying to do is, we have n observations of xi, 1 to n, and it's a linear mixture of n independent component coming from S1, S2, Sn, and then it's really that how can we identify those components? And what we observe is really x. We don't know the s. S is something hidden, right? So idea is it possible that we come back with a relationship between all those hidden variables or hidden signals, which is S1 all the way to Sn, and use matrix A, multiply this S so that we saw our observation of X. We're trying to identify this A and the corresponding S. The main task is really to estimate the mixing matrix A and the unknown component of S. That's independent component analysis, objective of the independent component analysis. The main assumption for SJ are they must be mutually statistically independent and must be non-Gaussian. Otherwise, the ICA will not work. So idea is to find this A and S. And if we are able to find an approximation of A inverse, if we have an approximation of inverse, we use A inverse times X, we will come back with our S, the unknown component. The idea is really if we can find an estimate of A inverse. Once we find that, we use a W to represent that, we would be able to calculate our S based on the W. So that's the objective. Now we know that for any real matrix, it has this relationship. Again, it's linear algebra. We discussed in chapter 2. We also discussed a couple of times in this chapter as well. For any real matrix C, Cu equal to U alpha, and then if we use the eigenvalues lambda I to come back with this alpha, C would be the corresponding eigenvectors of all the corresponding eigenvectors. Put them together would be the C. put them into the U, larger U. So alpha is a diagonal matrix whose diagonal values are the eigenvalues of C, and its corresponding eigenvectors would put together will come back with an U. And then C is equal to U times D times U transpose. D is the diagonal eigenvalues. U is eigenvectors. So this is also called eigenvalue decomposition, EVD. Okay, one special case is we are able to scale X so that its variance becomes identity matrix. Instead of D, we use D negative a half to achieve the fact that its variance becomes identity matrix. And then in the textbook, it actually continues this discussion to see how we can leverage this powerful information of X tilde and C tilde to estimate the W. That's really the objective that we're trying to do. And then from there, we would be able to come back with A inverse and corresponding S. So here, I'm now going to continue more discussion. The point is really that you should understand, especially for the last 2 hours on SVD and ICA, just try to understand the high level. And a lot of software packages already implemented this. You could leverage those software packages directly. Understanding the underlying theory would be important so that when you run the analysis, you know what the algorithm is trying to do. Just more notes here. R has PCA and fast ICA packages that's already implemented there. Python has PCA, ICA from sklearn. And MATLAB have all the functionalities such as PCA, SVD, MNR fit, multinomial logistic regression. That's MNR fit for multinomial logistic regression. That's all for Chapter 5. Thank you.